I'm very delighted to be here to participate in this happy event. I thank the organizers for giving me this opportunity to be present in this center of the world. There was maybe there is a center is not unique, maybe. So there were some debates. But we met in another center, which you may call it a center of gravity, which is, I do not know which is more relevant, center, geometric center or center of gravity. Okay, thank you. So I just want to say a few words about Carlos and my long association with him. So we met each other long back in the corridors of Paris 6. At that time, so long back that at that time I had a reasonable amount of hair, and now you know. Natural processes. So apparently he was aware of my interest in homogenization, and he introduced himself in the corridor, and then we started discussions, and then immediately he posed the questions by Planchard. And then he already had done some work with Aguirre, and today morning you had a little bit of history of this episode, and that's how we started our collaboration, and the rest is history, which you know. So I have been visiting Chile for a long time, and several times, and we had a lot of discussions. You introduced me to your parents when they were alive, and then other members of the family who are not here today, but they were very kind to me, and I enjoyed their hospitality. And then you visited me several times in India. First time when you visited me, you were feeling sick without proper meat. And then slowly you changed. Now, of course, I see you are more health conscious. So that is the secret about people were conjecturing about his age. He is very health conscious. And Lola and myself, we used to mock at him when he insists on eating certain things in certain ways. He has always, firm opinion and views, even if he is not entirely correct. So, like the periodic structure here, you discuss with him one day, and then you think that you have convinced him, but then the following day you think that he has gone back to the old position, and you see that you have failed. And another thing which I wanted to say, yesterday there were some things about Einstein. Well, I see some features. Einstein preferred models which are simple but not simpler, depending on your objective. Well, I mean, you always, your approaches were simple even for a complicated problem, because you go into the fundamentals of the problem and then look for the structure there. And I would add one more, Dirac. Apart from Dirac insisted on selecting a model, the mathematical elegance the stories associated with the Dirac equation is there in the literature, one can read. So, his main selection criterion is mathematical elegance and beauty, and you also always looked for the similar features in your problem, in your proof, and we have been associated, we have discussed quite a long about all these things. And another thing that we discussed our big patron, if you like, Jacques Lilians. So, I just want to cite one sentence from him and then start with this. So, when the book he wrote with Bensusan and Papanicolaou, so only the draft was ready, and I was his student in Iniria. So, he gave me the draft and then asked me to read, okay, in particular, quatrième chapitre, fourth chapter. So, il y a 2000 problèmes, je cite Jacques Lilians, il y a 2000 problèmes dont le premier est de le comprendre. There are such a prophetic words, I would say, because at that time he felt that Papanicolaou, the way he has written, the way he has formulated the problem, the way he presented various ideas, Jacques Lilians was not happy at all. And now you know that, that the fourth chapter has given rise to several developments later on. And so we used to discuss all these, recall all these things, and we discussed, and I thank you for giving me the opportunity and your long association over the years. Thank you very much. Okay, so let me begin this dispersion. So, as you see that I have several collaborators here. Some of them are present in the hall. And the last one is Loredana. Well, I mean, it's her old family name. Now it's a different family name, but the joint papers have appeared with this name. So, this is the periodic medium. You have seen yesterday's movie, how the heterogeneities disappear as epsilon goes to 0, and then you have a homogenized medium. Okay, so I am going to present some aspects which are different from what other people have done, and my perspective is propagation of waves in such a medium. So, in particular, that fourth chapter in BLP. So, the first thing is that experimental observation. So, these are the names I picked up in the literature. So, when waves propagate for small times, there is no dispersion. That means that propagation does not depend on the wavelength for some time, okay? And then for large times, you see a bifurcation, you see different behavior of propagation of waves depending on the wavelength, so which is called dispersion. Okay, so here is the model. So you have the usual acoustic wave equation with this A epsilon. So you have A epsilon is the usual divergence form operator with oscillating coefficients, and you have the same operator at epsilon equal to 1, which is denoted by A, and these are the usual ellipticity hypothesis. So, in order to have this property, it is reasonable to start with this kind of model, and then in order to have the dispersion property for large times, you must analyze this as epsilon goes to 0 and then show dispersion. Okay, so in other words, the model we are looking for is not just a homogenized medium, because the homogenized equation, the corresponding dispersion relation is trivial. That's what I meant when I wrote that sentence. So it is not going to model dispersion. So we are looking for a macro model which has a nonlinear dispersion, non-trivial dispersion relation, at the same time well posed even for small scales, even for all scales. Yeah. So this is the model we start with, and then this is kind of assumption is made for simplicity because it contains essential difficulties. So we have f here, we have 0 there with a band limited f. Okay. So this is the typical model in application, which is called the two-phase model with a given proportion gamma. Alpha 0, alpha 1 are the phases. Okay. So this is the usual homogenization problem which you have seen yesterday in Loredana's presentation. So I don't go into the details. Maybe if necessary I will come back for the notation. So what is important is that you can homogenize the operator, and then you have the corresponding homogenized operator which is denoted by Q here, and these are the homogenized coefficients. Okay. Now in the case of 1D, some simple things occur. So in particular, homogenized coefficient you can compute explicitly for the two-phase medium, which is nothing but the harmonic mean of alpha 0 and alpha 1 taken in the proportion 1 minus gamma and gamma. So in particular, you don't see any presence of microstructure here. Okay. So here is the big theorem, which is found in many sources. So in particular, Bensusan-Lyons Papanicolaou, Sanchez Palencia, and also more recently, comparatively, the paper by Francois Mira, Frankfurt, and Brahim Utsman. Okay, so this is the homogenization theorem for wave equation. So the amplitude and the momentum, they converge weakly to the solution U, which satisfies the acoustic equation in the homogenized equation, homogenized operator, homogenized medium. Okay, so this is the basic result. So you see the dispersion relation corresponding to this operator is trivial because Q has a constant coefficient. Okay, so in order to capture dispersion, we have to go beyond this. So there are several ways, several techniques. So you have you can go look for strong convergence in the energy norm. Homogenization theorem as such gives you only weak convergence, and there you have a notion of characters, and this works if you have parabolic problem, elliptic problem, because they are dissipative, and it's not working if you have a conservative system like the wave equation. Even if you include the characters which are suitable for elliptic and parabolic problem, there is always some residue field which is very oscillatory, and this thing has been analyzed by Francois and Frankfurt in favorable circumstances using H measure. Okay. Full amplitude and its behavior is open. Only the intensity of the amplitude can be done in some favorable cases. If you have completely oscillating coefficients, the problem is open. Okay, but we ask a different question. We don't ask for behavior of all the waves. What we want to capture only the dispersion. So the question is the following: can you define a macro dispersion coefficient and the corresponding operator which captures the dispersion? So there may be several complicated effects. We want to capture only the order beyond homogenization, that is all. Now, so here is where the idea of block waves, which of course was introduced in this field by Carlos Conca and Aguirre. Okay, this is very helpful because as you see that there is a hierarchy of decomposition which is possible in block wave approach. Okay, so this is, so what are the block waves? You have seen it in Loredana's talk, you have seen it in Gregoire's talk, and you see it in mine, and you will see again in Carlos' talk. So if there is Carlos Conca, there is going to be block wave. So you cannot, maybe a little bit overdose, but okay. So block waves are simply correspond to Fourier waves, exponential Fourier waves for homogenized medium, and the counterpart in periodic medium is precisely block wave. Okay. Now, so they are the standing waves, if you like, in the periodic medium. Now, how they look like? So these are the in the homogeneous medium, Fourier waves. It is not exactly the same, there is something. So it is a perturbation, but it is a multiplicative perturbation. This is the basic philosophy, basic ansatz of behavior of periodic medium by Floquet. So same. Okay, so we have not only block waves, but also the corresponding energies, and the energies are denoted by lambda, eta. Eta was the parameter in the dual torus which was introduced today morning, so I do not want to repeat all those things. What is relevant for homogenization is m equal to 1, okay, the first energy mode. Beyond that, of course, if you want to capture higher order, higher energy phenomena, that will be necessary, but here we are going to look at only the lowest part of the energy. Okay, so m equal to 1, so there are two indices, that is the difference between the usual homogeneous media where there is only eta, which physically signifies the momentum parameter, whereas here you have energy also. So there are two parameters, m and eta. M signifies the level, energy level, and eta corresponding momentum parameter. Okay, what's important is that when eta equal to 0, so not only we look at the lowest energy, but also small momentum. So when you do that, there are some nice things which happen. In particular, the lowest energy and the lowest mode, block mode, they have some analytic property. This is the fundamental thing. This is what you have a hierarchy of complications added to the homogeneous medium, and this is the secret of success of using block modes. Okay, so here is the analytic property and the corresponding Taylor expansion of the energy and the block mode. And what happens is that as mentioned today morning, you recover all the results of in the homogenized case. So if you look at the Hessian, the double derivative of the energy, it gives you the homogenized matrix, and the characters are obtained by differentiating the corresponding block mode. So in other words, you have a big universe, block waves. If it's the infinitesimal approximation near eta equal to 0 gives you your old objects. And there are a lot of things inside the block world, which is up to you to exploit. So it's a very small information around eta equal to 0 gives you all the classical result. But the big assumption here is the medium is periodic. If you destroy the periodicity by means of interface or defects, you have seen a lot of complications. Okay, so why to stop with looking at the second order derivative? Go further to capture dispersion. So, exactly. So, the new object here is this fourth order. I have written several things, but then the new object here is the fourth order derivative of the lower energy lambda 1 eta at eta equal to 0. Okay. So, so using that, can one produce an approximate solution capturing the dispersion? That is the main objective. Okay. So, here is the attempt. So, first approximation. So, you decompose your solution. This is the u epsilon of the first slide, acoustic amplitudes, in terms of block modes with certain coefficients which are analogous to the usual Fourier coefficients in the homogeneous medium. Okay, as I said that there is superposition with respect to energy level and also with respect to momentum. Okay. Now, for homogenization, you have to take m equal to 1, I told you. So, all the higher energy modes you neglect. So, you have only one unknown here, which is this, the first block coefficient. Now, since the operator has been diagonalized, the equation, acoustic equation becomes a scalar equation like that, and then with the corresponding things for the initial data. Now, this initial data will be the first block transform of f, okay, f. So, this is the first block transform at a epsilon scale of f, which is an approximation to the usual Fourier transform. Okay. So, you have a simple ODE with the coefficient depending on epsilon, and there is a nice analytic property near eta equal to 0 here. So, you have an expansion like that, and the expansion, the idea is to go beyond the second order, which is the homogeneous part. So, include the next order, which is possible, and then these are all error terms which we will omit, and here there is some approximation that is also part of the homogenization. The first block transform converges to the usual Fourier transform. Okay. So, with that, one can suggest an approximation to this expression on the integral expression on the right hand side. So, which is given by this. So, it looks complicated, but you see Fourier transform occurs, and then homogenized coefficient q occurs, and then this the fourth order derivative d occurs. And if you look at the equation satisfied by this v epsilon, it has this homogenized part plus this term with some error, which is what is expected. Okay. Now, the difficulty with this, so you seem to have solved the dispersion problem. You have this is macro dispersion equation, because it is a constant coefficient. This is also constant coefficient. There is no x involved. Okay. So, it looks nice that you have solved the problem, but no. This is a surprising result which we could prove the help of Rafael Uribe. This coefficient here, this is the highest order term, biharmonic type of term with this tensor there, fourth order tensor. It has the wrong sign. It has the wrong sign. D is less than or equal to 0. And this is true universally. That means independent of the microstructure. Whatever be the microstructure, this is true. And this is something which came as a thunderbolt, is a big shock for us. So, we have unconditionally ill-posed problem, always ill-posed. No way you can repair this. Okay. We will see whether we can repair it or not. So, we have an ill-posed equation coming from a well-posed problem, but of course, you have an explicit solution v epsilon. I have given you the expression, but the thing is that unfortunately, if you want to do any numerical approximation, you do not know it, even though that expression is valid, since you have ill-posedness, the numerical approximation can generate small scales, and it's useless. Even though you have explicit expression, it is useless. So, okay, these are the slides to prove D is negative. I don't go into the details. So, if you look at the literature where such a natural approximation procedure gives rise to ill-posed equation from a well-posed one, the first occurrence, in my opinion, occurred when Boussinesq analyzed water waves, and then he was trying to suggest approximation. So, there are some recent literature on that by Mogin and his co-authors. Now, they have remedied the situation. They have remedied the situation. They have, in other words, removed the difficulty of ill-posedness by playing around with a trick. They interchanged partial derivatives and time derivatives judiciously in order to get a well-posed equation. Mogin calls it the Boussinesq paradigm. Okay. Now, this procedure has been recently carried out in periodic structure. Of course, the original one for water waves. So, for a periodic structure, the kind of equation, acoustic equation, this has been done in a more rigorous footing. So, again, I picked up these names, Askes and his collaborators in Great Britain. So, this interchange of spatial and time derivatives is done using Paddy approximation. So, you have a concrete approximation, rational approximation procedure. And then later, Agnes Lamache and her collaborators in Germany, they have done it in full generality. This one is particular cases. And I just want to give you a couple of points on the approach of Lamache. So, there are two steps in the approach. One of them is, so you have this bad tensor with this fourth order derivative. So, you split it like this, you split it like this. In some sense, you divide this by Q is positive. You divide by this operator, and this is a quotient and this is a remainder. And you can do it in such a way that this E is with a negative sign, here it is positive, and F is also positive. So, in other words, this is the fourth order term. So, this should be compared with that. This was negative, now it is positive. So, in other words, the ill-posedness has been removed. But it is not enough, because that part is okay for, but there is also, we have to remove it at all scales. So, this is the Boussinesq idea. So, I said judiciously. So, you have to change x derivatives into t derivatives. So, you do it, first do this decomposition, and then here, you see, you replace this by, because the homogenized equation is satisfied. So, dou t square u equal to q dou x square. So, I can replace this combination by dou t square. So, this is the idea. So, a kind of curious closure scheme to change the behavior of these small scales. So, as a result, when you do that, so the whole equation, dispersion equation here, which is ill-posed, now for that I replace by this Boussinesq trick, you have this. Okay. Now, things are well posed. So, W epsilon for any initial, this initial value problem is well posed, because I told you that this has favorable sign, and not only that, it has non-trivial dispersion relation. Okay. So, this is the main idea. So this non-trivial dispersion relation is due to this Boussinesq trick. So in W epsilon, this is the solution here, approximates the old V epsilon, which already approximated U epsilon, which is the original equation, exact solution. At the same time, it changes the behavior of the short scale, so that the equation remains, equation becomes well posed. Okay. Now the next step, so the important thing is that there is this presence of this fourth order block tensor, which is here, but then this is a complicated algebraic computations here. The exact information got lost. Now in order to recuperate this information, what one can do, follow the procedure in the history, namely, since the Boussinesq periodic equation, I call this Boussinesq equation for periodic structures. Since it is of second order, so in time, so we have two families of waves propagating. So it is a bidirectional water waves type of equation. So you go back to the water wave literature, there was a model by Boussinesq for bidirectional water waves, and then Korteweg-de Vries reduced to more fundamental single wave propagation, and that is first order. Okay? And if you repeat that procedure, you get a third order equation here, not for the displacement but for the strain, I said that, and it is a third order equation, linear, and you get back your fourth order block tensor D. So in other words, if you look at one dimensional propagation, the more fundamental quantity is this block fourth order tensor. And if you look at the bidirectional things, it's so in other words, first of all, this procedure is very complicated, and you don't see D directly there. Okay, so this is the main thing. So I just want to end by recalling some of the things which I have been saying, or rather dreaming. So if you want to solve optimal design problem, you want to design a suitable microstructure and manipulate the corresponding dispersion coefficient, namely the various things here, right? You have E and F, they are all macro objects, R, D, which is here. These are all depending on the microstructure. So the objective in optimal design problem, as you know, is to manipulate this microstructure and have the required D, required type of dispersion. Okay, so this is the thing. Now, one obvious answer to this is to collect all possible behavior. You vary the microstructure, you collect all possible macro dispersion coefficient, and given any macro coefficient, you must know what is the underlying microstructure. So this is a big catalog. Okay, catalog. If you can form this catalog, then everything is fine. Okay. Now such a program is not new. Of course, it has been carried out for the homogenized coefficient by several experts who are sitting right here. So I reproduce their inequalities and their world famous figure. Okay, so this is the all possible behavior, including various uncertainties in the position of the microgeometry, and all possible things are contained in this convex lens shaped region for Q with a certain constant proportion gamma. Okay. And I just want to point out that there are some critical points here. So these things, the corresponding underlying microstructure are laminates. So here the corresponding thing is a Hashing microstructure. Okay, so these are the important microstructures which decide, which determine this figure. So, our dream is to carry out a similar program for the fourth order tensor, which is the fundamental quantity for one dimensional wave propagation with the dispersion in periodic medium. Okay, this is a dream. Okay, but yesterday you have seen in Loredana's talk how this quantity behaves when when the dimension equal to 1. This is the case which has been completely solved. Not only we have the extreme values, negative values up to 0 for D. So, this is the expression which you have seen yesterday along with the graph, but she forgot to mention one thing, namely what is the underlying microstructure. Okay. So, we are interested in this negative value. So, what is the underlying structure which gives rise to this particular value? Okay. So, curiously it is a classical microstructure, it is not a relaxed microstructure. Usually in homogenization problem, the characteristic function chi becomes a theta, theta which takes values between 0 and 1. But among all possible microstructures for Q, which is everything in one dimension, all the things give rise to the same value for Q. That is what I remarked earlier. This is the microstructure people who cannot see. So, it is a characteristic function. This is the microstructure which is picked up by D to realize this extreme negative value. This is a very curious phenomenon. Okay. It is a very curious phenomenon. Okay. So, in other words, what we are saying is that you introduce more and more interfaces between the two phases alpha 0 and alpha 1, the value of D increases. So, here you start with one interface, namely characteristic function of one interval. You keep on adding more and more phases at the continuum, infinite number of phases, infinite number of interfaces, you reach D. Okay. So, reach D equal to 0, 0 value. So, at a minimum value we have just one interface, at a maximum value we have several a continuum of interface. So, the main principle from 1D or main lesson is that at the minimum value we have to minimize the interface area, and so we have a sort of isoperimetric problem. Okay. Now, so I said that Hashim microstructure here. So, what is the corresponding, so what is the microstructure chosen by D among the class of Hashim microstructure? So, in other words, this is the kind of program which is being carried out to analyze D. So, the study of D is that given a family of optimal microstructures for Q, what is the one which is chosen by D for its minimum value? So, this is answered only in 1D. In higher dimension, of course, it is conjecture. So, here is one conjecture. So, yesterday you have seen Loredana's talk about how this D behaves on laminates. So, here I show how it behaves on Hashim microstructure. Okay, I do not want to go into the details of Hashim microstructures. This is for the people who know. So, the one chosen by D is this particular Hashim microstructure, which we call Apollo Hashim microstructure. We want to minimize the interface. We want to minimize. We do not want to put too many core and coating inside. So, we want to have minimum number of things. So, this is the best way. So, I am looking at, so you have the entire R2 for instance, and filled with this kind of cubes, and I draw the core and coating like that. So, with the half side as radius, I draw like that, and then I have 4 circles, and I put one big circle in the middle, and then I put a smaller circle in the middle, and then I put this. So, it reminds you of classical construction of Apollonian circuits. So, this is the minimum parameter construction, minimum interface construction. So, this is the conjecture that, and maybe we are close to the solution, but okay, this is still a conjecture. Now, recently, we have been working on this problem. We have simplified enormously the approach of Lamarck's and so on and so forth. We have a very straightforward way to obtain a macro dispersion behavior, and the macro coefficient is very explicit. It's not like in their paper. It's very explicit, which you will see the D appearing there very explicitly, even in higher dimension. So that is the work in progress with Grégoire Haller and Marc Briand. I congratulate you for your this 60th birthday. Thank you. So the last one, only I can understand. It is in Tamil. Yeah.
So there was a very good idea to organize this conference in honor to Carlos. When I was invited by Grégoire Haller, I said immediately, yes, it's a very good idea to do it also in Spain, where you have a lot of links, familiar links also. And this is a subject about inverse problems in medical imaging. It's a subject in which Carlos is also interested. And I would say in Chile there's an increasing community of scientists working on inverse problems, young researchers, Jaime Ortega among them, and in other universities. One of them is Matthias Courdurier, and a student of Gunther Ullmann, who I remember Gunther Ullmann and Michael Vogelius contacted Carlos maybe in 2000, asking for students to go to the United States, taking some courses in inverse problems. And then I remember that Matthias was one of these, the first student going there. And then there was some collaborations, increasing collaboration with the United States, with Gunther and other, Michael Vogelius and other researchers. And it's a very interesting subject since it's connected with control theory. I don't know if it is connected with homogenization also, maybe, in the future. So, and it's also a very interdisciplinary subject in which you can collaborate with people from other sciences, in medicine, in geophysics, in engineering. So Carlos was working a lot with Jaime in inverse problems linked to the detection of bodies inside the fluid. It's a rather different inverse problems. It's linked to the SPECT medical imaging. So I will explain what is SPECT and then just put the problem. So the SPECT imaging technique is rather simple. You have to take some radioactive liquid, and then your tissue begins to emit some gamma rays, and thus these gamma rays can be captured by an exterior camera, an exterior detector. Both the direction of these rays in red here, and also the energy of these rays. So you count the photons going to the camera, and then you can identify what they're called the ballistic photons, which are the photons that go from the source, which is here F, the radioactive source is F, directly to the camera. So the idea is just to identify, to determine this radioactive source from the ballistic photons. It's just that. So in order to have more information, this camera is turns around the patient. Okay, here the photo, you have this machine here which is turning, which is going around the patient, and then taking the measurements in all the directions and all the positions. But there's some problem. Yes, thank you. Which is that, in general, A is not known. Okay? Yes, all technology is not working. And the main difficulty is that the attenuation of the medium is not known. The attenuation of the medium is just the attenuation of photons, the natural attenuation of photons inside the body. But, okay, I will explain how they solve that, simply neglecting the attenuation. So the idea is to, this is used, I will show also transparency, is used since 2000 also year as a technique, a very common technique in cancer treatment, and also in order to measure some activity in the brain. I will explain some applications. But what is the mathematics of SPECT? So the mathematics of SPECT is a very well-known equation, which is called the radiative transfer equation. Here is simplified, okay? But basically, this equation is the transport of photons in some direction, okay, which is the direction in which the camera is, attenuated by a factor, A, which is unknown in general. This is the radiative source inside the body. And this is the scattering kernel, the scattering term, which means the photons are not going every time straight, but they can change direction in general after some collision. Okay. So in general, we have three unknowns in the problem. It's a complicated problem. What they do in SPECT? In SPECT, they suppose that the source is unknown, of course, but in order to have a solution, they neglect the scattering completely. So they consider that there are no scattering, and this term is zero. And for the attenuation, they try to obtain the attenuation from other techniques, for instance, using computed tomography. So they use computed tomography in order to have the attenuation, and then they use this attenuation in the model, okay, in order to recover F. Well, okay, if we suppose that attenuation is known and K is zero, there's a very simple solution of this equation. We can just integrate, if you want, the source multiplied by an exponential attenuation given by A. It's very easy to solve the equation. And the solution is the integral of the source along lines and attenuated by some factor dependent on this attenuation A. And this is finally, when you integrate along the body, there's the detector. So the detector captures some integral of all this information along the line. And this is called the attenuated Radon transform. Yeah, the Radon transform is just the case where A is zero, the classical Radon transform without attenuation. And so if you have attenuation, you have the attenuated version. So the main problem in medical imaging for this technique is to invert this transform, so to obtain the source from these measurements. Suppose that you have these measurements for every position S. You have the origin, you have a direction theta, and then you take the orthogonal of the direction theta, you move in this direction, and also you have the angle. So you have two parameters, the position and the angle. And the Radon transform is a function of these two variables. Okay? So it's a transformation from R2 to R2. And there's a known solution, which is called the inverse, okay, for the attenuation transform, or the filtered back projection algorithm for the attenuated transform. And it's given by a procedure which is use some other transforms in order to compute from the measurements the original source. And this was theoretical for some years, but then recently, or in 2001, there was a numerical formula that was implemented in the scans, okay, in the real scans. So I will show you an example, which I found really interesting, is to study, in fact, treatment for Alzheimer's disease and for epileptic also seizures. What is the idea? The idea is that, in fact, why not using other techniques? For instance, to use MRI, is magnetic resonance imaging, or use computed tomography to see, okay, what is inside the body. And the problem is that for very, very low blood flows, you need this technique, since it's very sensitive to low blood flows. Okay? For instance, in this case, we have here different brain activities for a patient when the person is in a normal behavior, and then during an epileptic seizure. Okay? And during an epileptic seizure, you can see that the distribution of blood inside the brain is different. So you have regions with lower perfusion of blood and regions with higher perfusion of blood. So it is important to know which are the regions, okay, we have problems during the epileptic attack or seizure. Okay. And here is a movie. You can do this in 3D. Where's the here? So you can scan the brain, okay, from the top, and see which is the activity, the perfusion of blood activity into the brain with this technique. Okay, and this is not possible with the other techniques, since it's very, very, very it's a little, really little difference that can be captured with these methods. And this is used, for instance, in the hospitals in Chile, etc. It's also important for cancer treatment. When you are doing chemotherapy, you want to know what is the improvement after treatment, and then you also use this type of techniques to follow the patient between the different treatments. So it's a very useful technique. Okay. But what about reconstruct simultaneously the attenuation at the source? Why is it important for physicians to have the attenuation at the same time? Well, first of all, it's difficult sometimes to do a computed tomography before this. The ideal is to have the information at the same time. You can have movement of structures inside the body between one exam and the other exam, etc. So the main idea is to reference the source inside the body. The idea is the following. When you see the attenuation map, typically this is the distribution of organs inside the body. And then you can see where the source is exactly. So it's between two hemispheres, where is it exactly? So to reference the source, we need the attenuation at the same time. This is the idea, simultaneously. But there are no uniqueness of the inverse problem. You cannot obtain with these measurements the attenuation and the source simultaneously. Okay? But there are a lot of people trying to do it numerically. Even if you don't have attenuation, they put a priori information in order to have uniqueness. Okay? But a physician of the Catholic University suggests us to use some extra information they have from the experiments, or from the measurements. In fact, they have some information which is given by the scattered photons. In fact, the red part are the ballistic photons going directly to the camera, but you have also the scattered photons. We are going also to the camera. And you can identify the scattered photons by seeing the energy distribution of photons. In fact, the scattered photons have lower energy. So you can see, okay, these are scattered photons and this is ballistic photons. So you can distinguish between both or among them. So the idea is to do that, but if you consider scattering, you have to consider the coefficient k, which is unknown. So you have to assume something about this new coefficient k. And we say, okay, we will suppose just that k and a are related by a very simple, okay, relationship. So high spatial correlation among scattering here for simplicity is just a constant. Okay? We will see that this is not a non-physical assumption, in fact. It's very near to reality in several cases. And the idea is to consider the scattering as a superposition of first scattering, second scattering, third scattering, etc. And when you decompose the total intensity in the scatterings, etc., you can in fact write another time, okay, the radiative transfer equation used for SPECT, where you have, okay, the ballistic photons here given by the source, and then using the ballistic photons, you can use that as source to have the first scattering photons and then the second scattering photon, etc. Okay? And doing that, finally, we suppose that we have two measurements, in red and in blue. So in red, we have the ballistic photons given by the source directly, and in blue, we have the first scattering photons given by this term m, which is related to the ballistic photons. So you integrate the ballistic photons, and this is a new source to have the first scattering photons. And then now you have two measurements, not just one, two measurements you can obtain from experiments. And okay, so the natural conjecture is, do you have uniqueness now? And do you have a numerical procedure to compute the source and the attenuation simultaneously? So the inverse problems now is to recover, if you define the albedo operator, which is the operator that relates, okay, the parameters to measurements, if you have uniqueness. Okay? So you want to invert this operator. And the difficulties with respect to SPECT, of course, we cannot compute directly. We don't know A, so we cannot invert this operator in order to compute F from the attenuated Rado transform. So we have another equation. And now the problem is nonlinear in A. Before was linear. So the idea is to linearize. Before suicide, we have to linearize. So, in order to present the linearized problem, we need to introduce another tool, which is called the weighted Radon transform, in which you replace the attenuation by a general weight. Okay, but just the notation is I sub W. Remember that, and we have some half regularity gain with this type of transform, as is the case for the attenuated Rado transform, etc. These are pseudo differential operators. Okay. So the linearized inverse problem, this part is rather technical, but the idea is that you take, okay, a reference attenuation, a reference source, and you do perturbations delta A, delta F, and you compute the derivative of this nonlinear operator around this state, okay, and then you identify in this derivative two operators, L and Q, and the idea is to invert these operators L plus Q, this derivative locally. So, and why we divide into two? Since in general, if you suppose that A, okay, a check, not chapo, check. Huh? So I Axel check. Huh? So you take Axel check. The idea is that if A check is small, all this is small. Okay, this is the small part. And then if you know, okay, that in general, if you want to invert this operator, it's not so difficult, since the idea is, in order to invert this operator, okay, in order to have the values of delta A and delta if you equal to something, you can divide by m, okay, and then you know the value of delta A, and then you replace the value of delta A here, and you can have the value of delta f. So you have a procedure to invert if A check is small. So, well, this was the idea. So the main idea is to prove that L is invertible and Q is small with respect to the norm of A check. Okay? And this is exactly what we have to do. There are some technicalities. For instance, since you have to divide by this information coming from the ballistic part of the solution, the integral of the ballistic part, you have to suppose that the source is not nothing, is strictly positive and not exactly zero. And if you have some photons, then you will have some lower bound for the integral of photons, etc., and you can divide by m. Okay? Okay, there's some technical assumption, also regularity, enough regularity for A check and for F check, etc. And the idea is that to prove that this operator so is invertible, since Q is small, so the invertibility of L plus Q follows from the invertibility of L for A check small enough. Okay? And you can also show from this linearized uniqueness, you can prove the uniqueness for the nonlinear problem, but locally, as usually. Okay, so I will skip the proof, but just to say the main difficulty is to prove some estimates in fractional Sobolev spaces for these weighted radon transforms, etc. But it's just technical work. So I will show some numerical experiments. Okay. So this is the typical phantom, we call phantom, which when I started to do inverse problem, I think, okay, this is the lungs, this is the heart. No, nothing to do. This is in fact a phantom intended to be a brain, in fact. So these are the hemispheres, nothing to do with this part. And this is a typical source here. So the idea is that you have some radiative sources inside the brain, and you want to recover the source and the attenuation simultaneously. And this is the typical measurements. This is difficult to understand at the beginning, but is the angle, so it's the camera which is moving like this, and this is the position of the detector into the camera. Okay, so you have 2D observations for the ballistic, so direct rays, and from the scattered rays. And you can have error, or just in practice you have some Poisson error in the measurements.
That's measurements or that's scientific?
These are measurements. No. We will see real measurement. This is just synthetic for the moment. But yeah, and we add some Poisson noise since you count photons, so it's not really. And this is a synthetic example where you can see it's strange, but the exact red is not seen here, but there's the exact red circle and moon here, but you can see, due to the color, the exact red color is not shown. I don't know why, but this is the typical iteration. So this is classical spect. You can recover the source, but not the attenuation. And this is the first iteration of an iterative method. Okay, so when you iterate, you go closer and closer of the attenuation map here. So the idea is to superpose this reconstruction with this attenuation, and then you can localize where the source is with respect to the organs. We have tried to do something with real data, so we started with that. This was from real data. So what is the problem? You put a cylinder. We have several structures in the different layers. Okay, so you have some periodic structures and then some little or small objects, etc. And we compare the normal spect with this different spect, and this is the attenuation we obtain. So we didn't know if, okay, the first thing we noticed is that the error in the new reconstruction is small, okay, but it's difficult to see exactly. So we constructed an experimental setting, okay, in order to know exactly if it was working. It's okay. So we take some plastic cylinder, and we put inside some scattered. So a big scatterer, a medium scatterer, and a big scatterer, and a radioactive source. Okay. So the radioactive source is here. This is the big scatterer, the medium scatterer, and a pencil as a small scatter. Okay? And we put that in the machine and take measurements. Okay? So these are the results. So just for the attenuation, the source is very easy to locate. Okay? You can recover the source easily. But the difficult thing is to recover the attenuation of the media at the same time. So this is for the attenuation. So when you go through the object, at the beginning there's nothing, then you are in this part of the object where it's just okay, plastic, and then you pass, in this direction you pass, and you see at the end the objects. Okay, this is the idea. And here you can see nothing, then you see the cylinder here. So this is the exact cylinder, and this is the recovered cylinder. Then you begin to see the structures here. Here there's the hole where the source, the radioactive source is. Okay, you can see that, and the big scatter, and then you can see the two scatters. And if you have good view, there's yeah, there's just a very small point here, which is the pencil. And then, okay, also this is exact, but you can see here the big scatter, the medium, but you can see the pencil. Here the medium scatter is not seen, but you can see a little bit. So it's okay. The method is okay. You can recover, in practice, from real measurements, you can recover something. So there's a lot of things to do. In practice, we want to implement this method in real machines, as Carlos did. So I finished with this photo, which is a presentation of the portable echograph that they built with Carlos, with a colleague in the Department of Mathematical of Electrical Engineering, Manuel Duarte. Okay, and this was the demonstration of this equipment in the festival of Engineering and Sciences we had last October. Yes, and this is the stand of the Center of Mathematical Modeling showing this new technology. And so there's a patient here, and a real patient. And this is Carlos with the machine, which consists, in a portable echograph. This is the I don't know which is the name, the transductor. And this is these are, I think, glasses to see if you don't have a screen, you can have video game from Sony, maybe. Okay, so thank you, Carlos.
Okay, so we are about to finish. I wanted to make sure to thank everyone. Maybe I didn't do it enough in the opening of the conference, but now it's time to do it because everything was quite successful. Even dinner yesterday, it seems that the menu was at the level of what people expected in Basque cuisine. I wanted then to thank especially Irantzu Erespe, who is somewhere there, our executive secretary that took care of everything. This was really a Euskadi Chile workshop because Irantzu was the main organizers, but there were two persons, Jaime and Rodrigo, who is there, who really made everything. So for me it was really simple to follow. And we were very lucky because we had a lot of support from scientific committee. Greg in Paris was the third partner, also the organizing committee. But we also had plenty of sponsors that as soon as we said we were planning to organize something in honor of Carlos, they offered immediately financial support that was significant and allowed us to do this in this atmosphere, this place. So the first center I would like to mention is the Centro de Modelamiento Matemático in Universidad, Chile, the Basque Center for Applied Mathematics here in Bilbao, the European Research Council that through the advanced grant Numeri Waves that we are running in our team also offered financial support. The CONICIT, I understand this is like the Chilean, say, NSF, the CNRS, the French research network, ICEMAT, the Institute of Mathematics in Madrid. Rafa was here. I don't know whether he's still around. Rafa, yes. So thank you, Rafa. Then we also have the support from the Faculty of Engineering of the Universidad de Chile, the one that was founded by Gorbea, as you mentioned the other day. The ESMAI, the French Society for Applied Mathematics. The RESME, the Royal Society of Mathematics in Spain. This GDR, Groupement de Recherche for European network of research in control of PDs that was launched very efficiently by Fatih Alabo several years ago, and now is being run in France by Karim Bochard. The ECODE, the Institute for Control and Decision of Paris-Saclay. So this, as you know, France is doing a great effort to build around Saclay platform, where in particular Polytechnique is a new university. And then ECODE is a new lab oriented to control of PDs, or control in general, that is led by Yassine Chitour, and he was also very enthusiastic about supporting this initiative. The École Polytechnique, that was represented here by Greg Aller. The Basque government, Eusko Jaurlaritza. The Chilean Academy of Sciences, that was represented here at the highest level by Professor Asenjo, and the Laboratoire MAP5, c'est plus facile en français, coordinated by Annie Raoul, who I think is here also, and she was also very supportive. Maybe I am forgetting some other supports we had. We certainly did, but these are some of them, and I think it's a very good idea. Gives a very good idea of how broad the enthusiasm internationally was for the organization of this workshop. Okay, so this is the first time I see this picture. So this is the picture we took yesterday. You can recognize some people there. Okay, so maybe easier in the first row than up there. But let's hope that Photoshop can do something to improve. And I thought there was a last photo, but this is it. So this is the poster. The poster was done in. I find it particularly nice. It was done in the faculty in the CMM. I don't know who was the designer of this. Cristian Murillo. It was very, very successfully done. And well, thank you again.
Among all the honors I have received these days, there is this last one, which consisted in asking me to give the conference closing. I will speak about some mathematics connected with physics and connected with science, trying not to go into any details, technical details of what I have done in mathematics, because I have all my family here and I don't want to be in troubles with them. Since I have been asked to give this conference, I allowed myself to divide it into two parts. In the first part, I will go through some details of my career as mathematician, and I will go into more mathematical presentations of things in the second part of my presentation. So I will start with some biographical outline of my career, and to do that, I have chosen to link my career with my journeys. So I have chosen 2 or 3 journeys that have marked my personal life and my career as a mathematician. So the first trip was first important trip was in 1979. It was my trip to Paris. I went there to earn my PhD. I was supposed to be there for maximum 2 or 3 years, but I only came back almost 10 years after, 8 years and a half. So I stayed in Paris a very long time. It was maybe the most important trip and the most important experience I have had in my life. The second trip that was extremely important in my life was a trip I did in 1983. I was living in Paris at that time, and I visited Madrid, University Complutense. It was some kind of doorway to the Hispanic world and the flourishing Spanish school of applied mathematics in Spain. And the third trip was already mentioned this morning by Vani. It was between 1994 and 1995. I went for 3 months as a visiting researcher to Tata Institute of Fundamental Research in Mathematics at Bangalore, because the main warehouse of Tata it is in Bombay, and this one, Control L. It is better. Control L. Oh, okay. Later, no? We will do that later. At that time, the Tata Institute had a very charming building inside the wonderful India Institute of Science campus. The building shared at that time two areas. One area where we could find the institute itself, and a second area where there were visiting the rooms for the visiting researchers. So during my stay, I was living in this institute and working all the time, 24 hours a day and 7 days a week. It was a monastical experience, working all the day during all the time I was at work, even when I was sleeping. It was a very productive stay, and I will never forget it. I have never repeated that. Okay, so journeys open the mind. And if you are in a good mood, in the correct mood, and ready to learn, there is a whole world which reveals itself to you. And this is what happened to me when I arrived to Paris with the French School of Applied Mathematics. It was Fulbert Mignon who would incorporate me to Paris 6 and to the laboratory of numerical analysis and partial differential equations. This laboratory was founded by Jacques-Louis Lyons 10 years ago. I was arrived in October 1979, and the laboratory was founded 10 years ago in 1969. So here is Jacques-Louis Lyons, who was the founder of the laboratory. At that time, one was the classical path for any student in Paris was to follow the trajectory DEA, the DA, test de troisième cycle, and test d'état. I greatly enjoyed all this path under the guidance of eminent French professors, French researchers, and engineers. I had the privilege to be guided by multidisciplinary people coming from mathematics, more fundamental mathematics, from other sciences. I will show you which are the people who have been more influential in my career, and people coming from classical engineers. The first of my advisors was Jean-Pierre Pouel. I put here some of the guides he wrote at that time. So I kept them, yes. So you can see here that he was the first to introduce me to homogenization problems and this memory effect, okay, which has played a fundamental role all over my contribution in mathematics. But I was also, okay, I will use the word advisor in a very large sense, okay? Maybe we can replace the word advisor by influential people, okay? And the other one at the same level is Professor François Murat. He is here. He gave a very beautiful presentation this morning. And he introduced me to plenty of different subjects. And here is his handwriting, which is typical. I recognized him much more by his right hand, by the handwriting, than from the pictures. For example, he introduced me to this Sive-Stokes problem, which is linked, of course, with homogenization, but also to these non-classical boundary conditions linked with Navier-Stokes equations, okay? In particular with these flux imposed boundary conditions, which allows me to introduce this bilinear form in which you don't have the classical gradient-gradient operator, but you have rotational. And this bilinear form has a kernel, which is not equal to 0, it is not elliptic, and there is some interesting mathematics to be done. So, well, you know both of them, and you can easily imagine the great privilege I had to be connected with François and Jean-Pierre, and to receive their warm friendship at the same time as its scientific guidance. But they not only introduced me to mathematics, but also to this big family around Professor Lyons. And all what at that time was around him. He was the chairman of a seminar, a one-week seminar at Collège de France. He had plenty of PhD students with whom I could discuss, and former students that were also enormously influential in my career. And three of them are, first, fundamental mathematicians in France, Luc Tartare. Here he was explaining me that if you want to pass to the limits in Navier-Stokes equations, you will not have enough a priori estimates, and you need to use this compensated compactness of Murat-Tartare. From the mechanical side, there is a Spanish engineer, originally Enrique Sánchez Palencia. Today he has changed to Évariste Sánchez Palencia. He also taught me several ideas technical ideas on how to tackle important questions in mechanics linked with mathematics. In particular, the matching asymptotic expansions. It was Sanchez Palencia who gave me this idea in order to treat this Stokes problem, who was suggested by Francois very early in my career. But another interaction which was extremely fruitful was with Jacques Blanchard. This morning, Grégoire Allaire, he was speaking about this kind of mathematical models in order to understand vibrations of tubes inside the condensers at EDF. And here, there is this celebrated non-local boundary conditions in which there is the integral of the force around on the boundary of the tube. And when you try to homogenize this kind of model, as was said by Grégoire this morning, classical homogenization doesn't work. And you need to do something else. And this was the starting point for this block decomposition. Okay. But those were really maybe my very best years in my career. Those were, we can say, golden years in my training. But of course, nothing of that would be what it is if I didn't meet Lola. In 1982, no? And we get married in December 30, 1984, so 2 years after. And 5 years later, Maite was born. This was a special day because not only Maite was born, but some of you were in Chile at that moment because we were closing the second Franco-Chilean Congress on Applied Mathematics. In particular, Jean-Pierre was there, Grégoire was there, and maybe Eric, no, Eric, Fulbert was there, yes. Fulbert was there. Sylvie Masgalic. Okay. Now I will go through a little bit of mathematics without any technicality. And the starting point is this complex exponential. This is maybe the most seminal idea that mathematicians have had all over their life. And this idea was concretized by Leonhard Euler. In his book, Elements of Algebra, Euler introduced this notation, I equals square root of -1. This is something that make a big difference between mathematicians and any other researcher that they do not understand very well what that means. This is something that lives in mathematical minds, but not in other. It is only in mathematicians that this number exists. Okay? This is some kind of abstraction that if you are not mathematician, it's very difficult to do it. Okay? And in a second book, in the book Introduction to Analysis of the Infinite, he was able to understand how complex exponential can be expressed by trigonometric functions, and he proved the theorem. He proved the theorem that says that the complex exponential e to the power I theta is equal to cosinus theta plus I sinus theta. And here he was able to connect two mathematical words: Greek trigonometry and complex mathematical analysis. Okay? If you, instead of e to the power I theta, you name that phi, as the complex variable phi, you touch two big words, in two big dots in mathematics, which is complex variable and plane waves, because cosinus theta and sinus theta are the classical plane waves. So this is the starting point of mathematical physics. Plane waves on the right-hand side of the equality, and complex mathematical analysis on the left-hand side of this equality. So this was a miraculous connection. And today one can ask this question: is there in physics or in nature maybe something that is not a wave propagating somewhere? Maybe if you want to say that the answer is yes, so there are things that are not waves propagating somewhere, the only thing I can imagine is gravity. And why I can imagine gravity as not a wave propagating somewhere? Because we don't know which is the nature of gravity. It is still an open question. Physicists, they don't know what is gravity or which is the nature of gravity. So maybe gravity is not a wave propagating somewhere. But so thanks to this identity, we can link mathematics with physics. And for people which are not mathematicians, let me say that if you take theta equal to pi, you get this celebrated formula, e to the power I pi plus 1 equals 0, which is maybe the most beautiful formula we can find anywhere. Why it is beautiful for mathematicians, at least? Because in this formula, we have all our main pet symbols. There is E, there is pi, there is I, there is 1, there is 0, there is plus, and there is equal. So there is mathematics is concentrated there. Okay. So this is the first role played by this complex exponential. And the second one is in the other sense. It is here, Fourier transform. It has been mentioned several times in the last lectures. Fourier transform, it is named for Joseph Fourier, which it is maybe the main actor of something that every mathematician tried to do, which is to mathematicize the world, the real world. In his celebrated book, Théorie analytique de la chaleur, he wrote in Latin this sentence, which in English can be translated as numbers govern the fire, saying that numbers govern the nature or governs nature. Okay, this is in some way he was restating what was already said by Galileo. Galileo, he was convinced that in order to understand nature, you need first to understand mathematics, the symbols behind nature. Okay, it's not Fourier who got this formula, but in the case of periodic functions, Fourier was able to obtain a formula which is similar to this one, but which is simpler. Okay? In this formula, you use all the frequencies, in fact, or all the plane waves, all the complex exponential. D'accord? Okay? And if U is periodic, this Fourier transform, or this integral, becomes just a sum of a discrete number of frequencies. And this is the celebrated Fourier series coefficient expansion of U, in which what you do is to decompose any function U in an elementary oscillations or the so-called plane waves, which is this complex exponential. Inversely, one can recover the Fourier transform starting from the Fourier series of the function U truncated between minus tau, and next letting tau goes to infinity. So there is some kind of equivalence between the general case in which U is not periodic and the case in which U is periodic. Okay? So periodicity is very close to non-periodicity, playing with the length of the period. Let me say that Fourier analysis has many applications. I am short saying that it has many applications. Maybe this is the most successful mathematical idea that has been used to explain physical phenomena, and not only physical phenomena, but also in engineering. Which is the main virtue of Fourier analysis. It connects two other big universes. The universe in which one studies natural phenomena and its mathematical modeling, and also its method of resolution. So here you can connect via Fourier transform at least 3 big dots: natural phenomena, mathematical modeling, and method of resolution. Now, when you look at Fourier transform, in the way we are going to do it in the next slide, you will see that Fourier analysis, it is behind the Fourier analysis, it is implicitly the fact that waves are propagating in a homogeneous media. Okay? And the question was how to this Fourier analysis would be generalized to the case of a general heterogeneous media. We don't have a complete answer to that, but at least in the periodic case, with a period arbitrary, we can start saying how to generalize this approach. So to do that, this was done in different presentations before me. It was done by Loredana, next by Vani, and also by Greg. And the idea is to start considering wave equation in the full space, look for solution by separation of variables, and to obtain the spectral resolution of minus Laplacian in the full space. Plane waves, so this complex exponential, can be regarded as generalized eigenfunctions with eigenvalue lambda equal to square of the frequency. Okay? Minus Laplacian has a continuous spectrum, which is 0 plus infinity. The plane wave is not a classical eigenfunction because it is not in L2, but it satisfies this spectral equation minus Laplacian of the plane wave. It is equal to absolute value of psi squared times the plane wave. But these plane waves, they expand some kind of base for L2 functions, or so functions with finite energy, in the sense of Fourier inversion. Any function u can be written as a linear combination, let's say, of plane waves, where the coefficients are given by the Fourier transform of the function u. Okay? And which is, it was Gregoire this morning who said that using these plane waves, one can find the spectral resolution of the operator minus Laplacian using truncations of the Fourier transforms. So the family of projections that produce the spectral resolution of minus Laplacian, it is given by this formula which is here. Okay? And the question now is how we can extend or generalize this picture to the case of a non-homogeneous medium. And the answer is quite simple. and it uses these block waves. So we consider now a periodic heterogeneous medium, which is represented now not by minus Laplacian, but by a more general differential operator with periodic coefficients AKL of x. And each of these coefficients is assumed to be periodic. And, well, which is the question we can ask is to know which are going to be the functions that play an analogous role as plane waves played in the case of an homogeneous medium. And these generalized eigenfunctions are these block waves, which are named for the Swiss physicist Felix Bloch, who introduced this kind of functions in a paper of 1928. He was studying the propagation of waves in electrons, the propagation of electrons in a periodic structure, and they are solution then of an eigenvalue problem which is similar to the one satisfied by plane waves. Today, these plane waves, they have plenty of applications in physics, but not only in physics, but also, as was mentioned by Gregoire this morning, in fluid-solid interactions in order to understand vibrations of tube bundles in nuclear condensers. If we add these Floquet ansatz, which means that we are looking for the wave equation solutions in the form of this ansatz, which is also some kind of separation of variables, but it is not exactly a separation of variables because both functions depend on both variables. So it is not really a separation, it is just a multiplicative ansatz. The spectral equation for A is transformed into a more simple boundary condition for the eigenfunction, but a more complicated operator, which we call it the shift operator. Okay, I don't want to go into the details of the applications that these ideas have had in the past. I would just say that we have applied this the block decomposition in order to understand homogenization problems. And just 2 or 3 things about homogenization. Let us say that homogenization is a central question in physics. It has been studied during more than 100 years. And the first result in homogenization that I know are these famous Clausius-Maxwell-Mossotti formula, who were derived in the case of conductivity. And Mathematicians appears in this picture a little later with the works by De Giorgi and Spagnolo. And this block wave decomposition has resulted in several applications, which are here, most of them to understand physical problems and physical issues. Gregoire Allaire and Vanni and Loredana, they explained some of them in their conferences. instead of going into any of the details of the applications that this approach has been able to produce results, I would like just to appeal to memorize, just to remember two dialogues we have. One of them was recalled this morning by Bunny. We had with Jacques Lyons concerning what we were developing at that time. These two dialogues are the following one. This is the dialogue that Bunny, remember, asked this morning. He approaches Jacques Lyons to comment on chapter 4 of his book, Bensoussan Lyons Papa Nicolau. So he said him, il est très joli le chapitre 4 de BLP. And Jacques Lyons said him, le quatrième chapitre a été rédigé par Georges Papa Nicolau. Personne ne le comprend tout entier. And Bunny, oui, vous n'avez pas tort, c'est dur. And Jacques Lyons answered, il y a 2000 problèmes ouverts dans le chapitre 4, dont le premier est de comprendre. And the second one, it was the following. I approached Jacques Lyons to comment on a Parseval's like type inequality that we had used with Greg. And I said him, grâce au son de bloc, avec Allaire, on a pu donner réponse à un problème industriel posé par Planchard à EDF. Jacques Lyons répond, oui, 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 je sais, votre papier est bien écrit. Sinon, à propos des sons de bloc, il y a une note d'Israël Gelfand des années 50 où se trouve une identité de Parseval généralisée. Alors moi je lui dis, d'accord, je vais regarder. And here you can see the photocopy of Gelfand's paper, okay? And somewhere he was right. There is some kind of Parseval identity inside, which is very similar to Fourier, to Bessel identity. Okay? And then, after that, he told me something that I have never forgotten. He said me, prenez les sons de bloc, l'homogénéisation et l'identité de Gelfand, et mettez tout cela dans la même farine. I will never forget that. So the result of this recipe, it is well known today. Okay, I will finish with a joke concerning applied mathematics and applications of more pure fields into less pure fields. So sociology is just applied psychology. Psychology is just applied biology. Biology is just applied chemistry, which is just applied physics. It is nice to be on top. This is what a physicist would also say. And what about mathematicians? Oh, hey, I didn't see you guys all day way over there. Okay. Thank you for everything. By years of warm friendship, for the joy of collaborative work, for the mathematics we have understood together. My warmest thanks to all of the speakers, to both the scientific and organizing committees, to Magali, and Iranzu. Thank you very much.
The conference now is closed. I wanted to show you, I know most of you are going back. Most of you are going back, and we wish you a safe trip. These are important days, almost Christmas time. Some of you have to do a long trip to go back to your duties, yeah, your regular life in Chile, which is how many kilometers? Like 7,000 or 7,000? Many of you are coming from closer, but in view of the weather conditions, the wind, well, it can be funny also to get to places like Paris or so. Okay, so I thank you very much for attending the conference. I should say also that in the organization of this conference, we always enjoyed of the, how you say, no, complicity of Maite and Lola that were giving us confidential information that was very useful to retrieve the career and the life of Carlos. In case some of you are staying around for a few days or you have some time to travel around, well, this is a map that will help you, finding your path. Okay, thank you again.
Show you one picture of how this began. This began during in Chicago. One day we are talking with Carlos, and we decided to organize this nice conference. Fortunately, Enrique has a visit to Santiago. You spend around 1 month in Santiago, and we began to organize. My laptop is starting. Always more slow. But I want to say, firstly, thank to Enrique, thank to Iranzu, thank everybody to be here. Thanks to Carlos also for the friendship for several years. I know you around 20 years ago, more or less. Okay, and thank you all from the Chilean side. I'm not sure that I can show the picture. But I'm going to say that this began in a small restaurant in Bella Vista 3. It's a Mexican restaurant, como agua para chocolate. And, well, no, I can't see, sorry. My battery is down. Okay, thanks to all. Okay.